In this problem solving session, I just like to do the following question. I have x and y having joint density fxy equal to 1 over 8 or xy plus 1 in the interval 0 to 2 for x, 0 to 2 for y, and 0 otherwise. So the density fxy is positive in a rectangle 0 to 2, 0 to 2. And the first thing I'd like to understand is I would like to find the marginal density of x and y. So these are called, this is the marginal density of x. So write this down, marginal of x. And this is the marginal of y. So now, so how does one go about doing this? So this is kind of straightforward calculations. Let's just do it step by step. So the first step is I need to understand what f sub x of x is. So f sub x of x is going to be what? You have to integrate out the y variable in fxy. So it's minus infinity fxy and dy. Just to make sure what we're integrating is understood. So x is a constant in the integration. We're integrating only y and fxy. But this we already know two things about. So this is equal to, so the first step is, so when x is outside 0, 2, this density is 0, right? And the density is only positive when both x and y are between 0 and 2. That's what it says here, right? And 0 otherwise. So the first thing we observe is this is equal to, so let me copy and paste that. This is equal to this person right here. So in the ranges from 0 to 2, when x is between 0 and 2, and it's 0 otherwise. That's also easy to observe, right? Because that's the only region where fxy is positive. But we can also do a little bit more jugglery. Let me just move this a little bit further down here. Move this further down here. And this one I'll just replace it by, I'll erase everything, and then the density is just 1/8. So 1/8 is a constant, or 1/8 x times y plus 1. So they're all constant, so I just put y plus 1. This is what I have, right? That's the density. That's what I have to compute. So that's quite easy to do also. So that's equal to, so let's write this down, everything in white now. So the same as this is equal to, so the only integration with respect to y here, right? So all you'll get is 1/8 x times y squared by 2. Y is from 0 to 2. And the other one is 1/8 times y from 0 to 2 when x is between 0 and 2 and 0 otherwise. Right. So what's that going to look like? That's going to be like, so it's like 1/8 times x, and if I put y equal to 2 here, so I'll get 4. 4 by 2 is 2, and then I have a 1/8, that's 4, and 2 is 1/4. So I'll just get 1/4 in both places. I'll get x, and here I'll get x plus 1. That's what I'll get. Because if I put 2 here, I get a 4. 4 goes in 8 2 times, and 2 times 2 is 4. Similarly, 2 here, 2 goes in 8 4 times, and the 0 part just becomes 0 on both sides. So that's it. And this is the density of x when x is between 0 and 2 and 0 otherwise. Very good. So that's the marginal density of x. So the question also asks us to find out the marginal density of y. So let's try and do that also. So there's a little trick to that, but let's just let's do it by brute force, and then come and check the thing again. So let me add the same template across. So now let me calculate f sub f of y. So again, f sub f sub y of y is the same as the integral from minus infinity f of x comma some y dx. So I keep y constant and I integrate out the x variable, right? So that's going to be equal to what now? That's going to be equal to, again, the same way as before. I'll do it in one step, in one short step, not 2 steps. So the same as integral from x goes from 0 to 2. The density is 1/8 of xy plus 1 dx. So y is here. Note I'm integrating our x variable, and this happens when y is between 0 and 2 and 0 otherwise. Okay. And what happens to this now? This is going to be equal to, if we just do the integration out properly, so I'll just get the first person integrator is 1/8. I'll get x squared by 2 times y from 0 to 2. So let's make this all white so that we know we're integrating the white part. And I'll have plus 1/8, the constant, and I'll get x from 0 to 2. Right? This happens when y is between 0 and 2 and it's 0 otherwise. Okay, it's quite nice. So what's that going to be equal to now? That's going to be equal to the same thing. So I'll have y by 8, I'll have 4 by 2, so 2, I have y by 4 plus 1 by 4. So the same thing as writing it as from 0 to less than y less than 2 and 0 otherwise. And that's the same as y plus 1 by 4 like before, or let me write down properly, reason it properly, same as 1/4 of y plus 1, then 0 is less than y by 2, between 0 and 2 and 0 otherwise. Okay, that's the density of y. So let's just do a little quick calculation. Let me just show you something, and then let's make a double window of this, and show you some interesting feature. We could have guessed this directly. So let's see how to do that. So for example, so what did we do? We found the density of x by this fashion. We integrate out the y variable, right? And found density of y by integrating out the x variable, right? So now if you notice, I got the same, essentially same answer. I got fxx is 1/4 x plus 1, fxy is 1/4 y plus 1, right? So one needn't have done this because this density is symmetric in x and y. If I change the roles x and y, it's symmetric. That's why the joint marginal density of x should look exactly the same as marginal density of y. You could use it also. So let me make the remark here. So I just make a small remark. One needn't have computed the density of y. Have computed the density of y. Why? One could have used the symmetric. Use the symmetry of fxy. To do this, after computing fxx. Because it's the same rule in that sense. That's a remark one can keep in mind. Of course, there's no harm in doing the computation again and getting the answer right. Okay, very good. So now now I want to ask the next question. What's the conditional density of fxy given fx given y equal to y, right? So now this is a simple computation, right? So we know this thing. We know that the density of x given y equal to y at the point x is given by f sub x comma y divided by f sub y at the point y, right? That's the formula, right? So let me make everything was fixed in orange. So y is equal to y is fixed. So y is fixed. So this whole thing is fixed. So these are all fixed numbers. Only x is changing, right? So for fixed y and y. So for y in 0 between y and 2. That's when the density is positive, right? So let me just make all this orange. So it's clear to you that y is fixed. And I'm just computing density of fx. So what's that going to be? That's going to be equal to fxy is what? Fxy is 1/8 of x times y plus 1. The whole thing divided by f sub y, which is 1/4 of y plus 1. Right, that's what the density of y looks like, right? And this holds true when what happens? when x is between 0 and 2. Otherwise, the top is 0, right? So when x is between 0 and 2, and 0 otherwise. Right, very nice. So that's the density. So we can rewrite this as, perhaps it's like xy plus 1 divided by 2 times y plus 1. When 0 is less than x, less than equal to 2, and 0 otherwise. Very nice. So now one simple question one can ask is, the next question one can ask is the third one, which I'll write down here. Are x and y independent? Okay. So there are two ways of verifying it. So one way is that you look at this person right here. You look at fxx, fxy. So let's copy fxy is this. So fxy is this. Let's bring it down all the way here. Paste it, make it a little smaller. So it's on one side. Let me put fyy on one side. This is fyy. So make it fyy. Make this orange so it is all consistent. And the next one is I'll make fxx. Let me go grab that up. That's up here. I grab it. I bring it down here. This, right? So clearly from these three guys, you can clearly check that fxy is not in product form of fxx times fyy. Right, for all x and y in 0 to, in fact, you can just check it. That's one way of checking it, right? You can just multiply it on check. The other way of doing it is, if you want to do it, so therefore x and y are not independent. Right. But the easier way to do it is, you can do it this way also. The easier way to do it is, this is one method. Right? The other way to do it is, you look at f of x given y equal to y at the point x. Right? This, if you look at it, look at the above right there, the expression, it depends on y, right? Because it depends on y. It depends on all y, right? Because y is fixed. So let me make all the y orange here just to make sure everything is consistent. So y is orange. So it depends on y. As y changes, the density changes. So this depends on y. This depends on y. So this also will immediately imply that x and y are not independent, right? So this also will immediately imply, let me erase this whole thing neatly. Also imply that x and y are not independent. Right, that's very cool. So this is one way of doing it like this, and another way of doing it like this. You observe this. Very cool. So this concludes this problem solving session. Just like if you have a joint density, you can compute the marginal density by integrating out the other variables. For x, you'll integrate out the y. For y, you'll integrate out the x to find the two marginals. To find the conditional, you just have to divide the joint density by the appropriate marginal density. And once you do this, then you'll have density, and then you can check independence by either checking fxy is not equal to fx times fy, or just verifying if the conditional density doesn't depend on another variable. So if it depends, then x and y are not independent. Very nice. Thank you.